Good morning, guys. Mr. Carver here. Today we're going to do section 3.9, differential approximation. All right, we will start off by just talking about what the differential form of a derivative is. We'll start off with an easy example. Let's say that f of x, actually, let me use this different notation. I'm just going to use y. So I've got y is equal to the cosine of 6x. All right, when I take the derivative of the left-hand side, if I'm going to derive with respect to x, remember the derivative of y is 1 times dy over dx. I derive the right-hand side, I have to use the chain rule because it's trig. I derive the cosine, that gives me negative sine, innermost function stays the same, times the derivative of the innermost function. And I can rewrite that as negative 6 times the sine of 6x. All right. Now, the differential form of a derivative does nothing more than bring this dx over to the other side. So dy dx is like a fraction. If I multiply both sides by dx, it cancels on the left-hand side and appears on the right-hand side. That's it. That's all you got to do. You derive as normal. You move the dx over to the other side, and this portion right here is the derivative, the differential form of a derivative. It's solved for dy. Now, you just need to be careful. Let's say you have a product rule like this, and I ask for the differential form of this derivative, or the derivative of this function, rather. The left-hand side, I get dy over dx. And the right-hand side, a little review of deriving now. We've got a product rule, right? So if I derive the first part here, remember that's chain rule, so that is x squared plus 2 to the positive 1/2 power. In fact, let me go ahead and rewrite it like that. Let's see if I can do this. It's all of that to the 1/2. It's a little easier to see that that is chain rule. So I derive the outermost function. That's going to be 1/2. Inside stays the same. Take 1 away from the power. Then I multiply it by the derivative of the innermost function. And I take the second, that's the cosecant of 4x. I take that as is. I now then want to add that to the first as is, that's x squared plus 2 to the 1/2 power. And now I want to derive the cosecant of 4x. That also is chain rule because it's trig. The derivative of the cosecant is negative cosecant times the cotangent. Remember, the innermost function stays the same. Now I've derived the outside. Now I derive the inside. Now, for differential form, remember what you want to do is you want to take dx and move it over to the right-hand side, but it's important that you multiply the entire thing by dx. So you've got to group that together in brackets. These brackets are very important. Everything gets multiplied by a dx. So this entire thing here is the differential form of a derivative of the original y function. All right, now let me show you why we need the differential form of a derivative, and it has to do with approximations. All right, for instance, we might want to use differentials to approximate the square root of 9.2. All right, let me draw you a picture here and show you how this all works. You'll notice that the square root of 9.2 is really close to the square root of 9. The authors are doing that purposefully. And let me draw a picture here of the square root function. All right, and now I'm going to exaggerate this drawing just ever so slightly. Let's call this 9 here. And we know that the square root of 9 then is 3. That's the corresponding y value. And then over here, let's call this 9.2. Again, not to scale. And this then is what I'm looking for. That doesn't look right. All right. So that's the y value I'm looking for right there. All right. Now, just let's talk about some of these distances. I don't know if you remember this, but way back this semester in Chapter 1, we talked about how to estimate the slope of a curve of a line. And the notation that we used back in the day was we used delta x. for change in x. So that is the distance from 9, in this case, to 9.2. And then likewise, this distance right here, from 3 up to the question mark, is going to be delta y. Now, let's say I wanted to know the slope right here at positive 9, the slope of the square root curve at positive 9. I could have taken these two dots just to estimate it, right? And I would do change in y over change in x. That would give me delta y over delta x. That's the slope of the curve right at 9. And if you also recall, the smaller dx and dy got, the closer and closer you got to the actual slope of, say, this blue line right here. All right, and the slope of that blue line can be noted by dy over dx, because remember, that's the notation of a derivative, which gives you the slope of the curve of y. All right, now, let's just say that I choose 9 and 9.2 to be my two dots along the blue curve here. So I'm going from 9 to 9.2. I think you would agree that the slope is dy over dx of the blue line. We've already said that, right? It's right here. Well, if I look at what my dy and my dx's are, would you agree that this is now my dx, and this distance right here is my dy, because it doesn't matter which 2 points on the blue line I pick, I always get the same slope, change in y over change in x. Well, check this out. If I extend this all the way over to the y-axis, now this is dy, and I still have a slope dy over dx. Now, I know this is not to scale, but if I were to make dx and dy smaller, I think you can see that dy and delta y will become essentially the same measurement. That is, this distance right here will be closer and closer and closer to this distance right here. As the closer these 2 points are together, or the smaller delta x is. Now, if this is confusing to you, you really don't need to understand it that deeply. What you want to know is that delta y over delta x is roughly equal to dy over dx. It's roughly equal to delta y, dy over dx. This is very, very important. Now, these problems will be written so that your dx value here is sufficiently small enough for this boxed statement to be true, that delta y over delta x is roughly equal to dy over dx. All right. Let me clear this up. Let me make some room here and show you then how to use this to work this problem. All right, so now I've redrawn the picture that I had before without all the other stuff making it confusing to look at. I think you would agree, just based on this picture here, that the square root of 9.2 is going to be equal to 3 plus, let's call this again, this is delta x, this is delta y, 3 plus delta y. If I start here at 3 and I add delta y onto it, I will get what I'm looking for here, which is the square root of 9.2. The problem is, I don't know what this is. I don't know that distance here. So I'm going to use differentials to approximate this distance here. So if I know that delta y is roughly equal to dy, could you also say the square root of 9.2 now is roughly equal to 3 plus dy? Because remember what we said before. We said that delta y over delta x, that's not delta x, that's delta x, is roughly equal to dy over dx. And when I say roughly equal to, I mean very close approximations of each other, which is why I can take delta y and replace it with dy. And the reason I want to replace it with dy is because while I don't know what this is, I can find dy. And let me show you how to find dy. I'm going to take my curve here, which is y is equal to the square root of x, and I'm going to write it in differential form. That's dy is equal to 1/2 x to the negative 1/2. And then remember, I moved the dx over to the other side. So this is the derivative in differential form. Now, I'm going to use that and replace dy with it. So now I can say the square root of 9.2 is roughly equal to 3 plus, the dy comes out, and I plug in this statement right there, which is 1 over 2 root x times dx. All right, and again, this is possible because this distance now right here is like dy, and this is dx. So if I take 3, that's this distance from here to here, and I add dy onto it, I will get this y value right there. All right, now you're almost finished. All you need to do is plug in some values here. So now I know that the square root of 9.2 is roughly equal to 3 plus 1 over 2 times the square root of x times dx. Now, we already know dx. That's the distance from here to here. So this is 0.2. And now the x value, I've got two x values. I've got 9 and 9.2. You want to use the one that you can actually square root, the one you know the value of, which is why I'm going to use 9 here. All right, and so now we can take our calculator, and I can come up with this approximation. And this gives me roughly equal to 3.03 repeating. Now, again, I know that you can just take your graphing calculator and you can just plug in the square root of 9.2. And the square root of 9.2 is 3.033150178. This is not what I'm looking for. I'm looking for your work here that shows me how you came up with this estimate right here. That's the differential approximation I'm looking for you to find. All right, I know that was a lot. Let me just work another one so you can kind of get a feel for how to use this. Hopefully it'll be a little more clear the second time through. All right, now we're going to use differentials to approximate 4.9 cubed. So you know that 4.9 cubed is roughly close to 5 cubed. Very, very close. So what I'm going to do then is I'm going to graph y is equal to x cubed. If I graph this, here's what I know. Got an increasing function. Looks something like that. And if this is 4.9, and this is 5, I know what 5 cubed is. 5 cubed is 125. This is what I'm looking for right there. 4.9 cubed. All right, now remember, just according to this drawing, this is delta x, that distance is delta y. And again, there's delta x, and here is delta y. And as I said before, the thing you need to know is that delta y and delta x are close approximations to, or can be approximated by, dy and dx. So there's my dx, and my dy, I haven't really drawn it, but it's close, right? This can also be thought of as dy right there. All right. So I think you would agree then that the value of 4.9 cubed is going to be equal to 125 minus delta y. But again, the problem is I don't know what this is. So I can use an approximation and say that 4.9 cubed is roughly equal to 125 minus dy. And how are we going to get dy? I'm going to find the differential form of the derivative of y. So when I derive that, I get dy over dx is equal to 3x squared. This comes over to the other side. So then 4.9 cubed is roughly equal to 125 minus 3x squared dx. All right, and now all I have to do is plug in some numbers. So I've got roughly equal to 125 minus 3. My x value, again, is the one that you know, so that's going to be 5 squared times dx, and dx in this case is going to be 0.1. And I can use my calculator and actually calculate that. That gives you 117.5. This is my approximation of 4.9 cubed. And if I just use my calculator and took 4.9 and cubed it, I end up getting 117.649. That's not what I'm looking for. I don't want an exact answer. I want a differential approximation assisted answer. And 117.5 is it. All right, let me give you another example of how this might work. Let's say that I have a cubical container. All right, so how about this? I measure the side of a cube to be 12 inches, but I could be off by plus or minus 1/16 of an inch. And the question is, how far off might my surface area calculation be? The assumption is that I'm going to be using differential approximation to help me with this. All right, so let's start off with the surface area of a cube. I'll let S be the surface area. And the surface area of a cube is just the sum of all the areas of the sides. Well, if it's a cube with all of side x, right, I've got 6 sides, and they are all x times x. So it is 6x squared. So if I were to graph this, 6x squared looks something like this. Now I measure it. Here's my side of my box. There's 12 inches there. And again, I could be off by plus or minus 1/16 of an inch, either above or below. So if this is my true surface area, I think you would agree that if I screw up the measurement of each one of the sides, I could be off by this distance, or I could be off by this distance. Now, according to what we had said earlier, this is delta x. These are delta y's. But I can't figure out what delta y's are. Using differential approximation, what I'm looking for really is dy in both directions, and these would be dx. All right, well, how do I get dy? I get dy by deriving my function. So if I take that and I derive it, I'm going to get dy is equal to 12x to the first dx. And by the way, I'm using y for s and x for x, obviously. All right, well, this is how far off my possible calculation of surface area could be. All I need to do is plug in some values here. So I've got dy is equal to 12, and I'm going to use the easier value that I know. I don't want to use 12 and 1/16. I want to use 12. But now my dx, that's where I use the 1/16. So my dy is off, or my dy is either plus or minus 144/16, which is plus or minus 9 square inches. And again, I could do this with a graphing calculator, right? I could just actually calculate the surface area of based upon a 12 and 1/16 side, and then subtract out the surface area I get when I find a surface area using a length of 12. But that would be an exact answer. That's not what I'm looking for. This is the differential approximation that I need. All right, now, if I take plus or minus 9 inches, and I want to know the percent error, and by the way, I guess before I move on to here, this is called propagated error. Again, propagated error. It's also known as resultant error or resulting error. Propagated error means exactly the same thing. So if you screw up an input, how far off could you possibly be for the output? That's called propagated error. Now, let's talk about percent error. Percent error is defined as propagated error divided by actual calculation times 100. So if I look at my prior example and I wanted to know the percent error, if I was off by plus or minus 1/16 of an inch, I'm going to take this, so that's 9 on the top, I'm going to use the actual measurement, but it's not the actual measurement of the side, it's the actual calculation of the surface area. So that's going to be 6 times 12 squared. Again, it's not the actual measurement of the side, it's the calculation of the function that you're using. And in this case, I'm using surface area. And then I take that and I multiply it by 100. And that gives me 1.042%. All right, now, guys, that should be enough to get you through tonight's homework. I'd be happy to help you when I see you guys next. Thanks much.